Acids are the substances which give a sharp, piercing taste. And Lavoisier first said, acid nature is due to the presence of oxygen. But later on, another idea came. People asked, hydrochloric acid does not contain oxygen, but it is acidic. So the idea was simply getting constructed. Arrhenius, actually his entire PhD thesis was on acids and bases, but his thesis was given passing minimum mark in those days. But later on, his findings found very important applications. So Arrhenius gave his idea on the existence of electrolytes. Electrolytes and non-electrolytes. Electrolytes are the substances which get dissociated into ions in aqueous solutions, whereas the non-electrolytes will not get dissociated. Say, for example, sodium chloride is an electrolyte. If you put a sodium chloride into a beaker containing water, immediately the sodium chloride will get dissolved and it will become sodium plus and Cl minus ions. But it does not mean that non-electrolytes won't dissolve. Non-electrolytes will also be dissolved. Say, for example, glucose is a non-electrolyte. Glucose is an organic substance, which is a non-electrolyte, which will not dissociate into ions. But if you put glucose into water, it will be dissolved. But that dissolution is due to the establishing of hydrogen bonds. But sodium chloride getting dissolved in water is due to the ionic atmosphere. Sodium plus will be engulfed by the oxygen atoms of the water, and Cl minus will be engulfed by the hydrogen atoms of the water. This is called the solvation process. The solvent molecules will surround up the particular ion according to the polarity difference. Therefore, substances mainly are divided into electrolytes and non-electrolytes. And the electrolytes can be divided into two types, namely strong electrolytes and weak electrolytes. Strong and weak. Look at this experimental setup. Very qualitative setup. You are connecting a bulb here, and one terminal of the bulb is dropped into the solution through a metal sheet, and the other end is connected to a battery, and then that also dropped into the solution as a metal sheet. Actually, when these two metals are connected, the circuit is closed and the bulb will glow. But these two terminals are not directly connected. They are immersed in a solution. Therefore, from this point to this point, it is metallic conduction. Whereas inside this, it is electrolytic conduction. Therefore, this electrolytic conduction will be very fast when more ions are present. This electrolytic conduction will be slow when less ions are present. Therefore, if more ions are present, more conductance, more current, therefore the bulb will glow bright. Only when less ions are present, less conductance, less current, therefore the bulb will glow dull. Therefore, if you take a standard concentration solution of weak and strong electrolytes, then you can understand. Suppose if you take 50 ml of water and put 1 gram of weak electrolyte and 1 gram of strong electrolyte separately. With the strong electrolyte, the bulb glows bright. With a weak electrolyte, the bulb glows dull. Therefore, this is how in olden days the nature of the electrolyte, whether it is strong or weak, was identified. Say, for example, if you take nitric acid. Nitric acid is getting dissociated into H plus and NO3 minus. This dissociation is a complete. This is complete dissociation. If you take 100 molecules of nitric acid, that will produce 100 H plus ions and 100 NO3 minus ions, and the dissociation is almost complete. This is called a strong electrolyte. At the same time, if you take nitrous acid, the H plus and NO2 minus, this dissociation is not complete because simultaneously association is also taking place. So this will get dissociated into H plus and NO2 minus, and H plus and NO2 minus will immediately start associating and it will form back HNO2. Therefore, this dissociation is not going to be complete even at infinite dilution. Even if you take a large amount of the solvent and go on diluting, even at infinite dilution, the nitrous acid will be in the undissociated form. So such things are called weak electrolytes. So according to Bronsted and Lowry principle, what we have seen is the Arrhenius theory. Arrhenius theory is mainly applicable for strong electrolytes, and it is not speaking about the inter-electronic forces existing. So there are so many limitations of Arrhenius theory. All these things we will be discussing in the electrochemistry in the 6th semester. But Arrhenius theory, it is holding good to some extent where it spoke only about the presence of electrolytes. The substances are made of oppositely charged particles. That was the fundamental idea of Arrhenius theory. Now, Bronsted and Lowry, they came with a new idea on acids and bases. And according to Bronsted and Lowry, acid is a proton donor and the base is a proton acceptor. According to Lewis' theory, acid is electron donor and the base is an electron acceptor. And yesterday itself we have seen ammonia is a base because ammonia has a lone pair of electron which can easily be donated. But when the ammonia, one hydrogen is replaced by a methyl group, what will happen? Methyl group will electron donate. Therefore, nitrogen becomes electron rich. Therefore, the lone pair of electron can be easily donated. When one more methyl group is also present, when one more methyl group is also present, therefore the substitution of methyl group into nitrogen will make the nitrogen more and more basic, because that makes the nitrogen donate the pair of electrons very easily. At the same time, if there is an acid, say for example, BF3 molecule, BF3 molecule, the boron is electron deficient because the fluorine is a highly electronegative, and the 3 fluorine atoms are pulling the electrons towards themselves in the BF3 molecule. Therefore, boron becomes more electronegative, means it can readily accept electrons. Therefore, something is I have changed. Base is electron donor and acid is electron acceptor. Just to change it in the presentation, base is electron donor and acid is electron acceptor. You have to change these 2 points. Acid is electron acceptor, base is electron donor. Therefore, BF3 is an electron acceptor, whereas NH3 is an electron donor. Therefore, NH3 is a base and BF3 is an acid. So next one, look at this. You should carefully look into this. H2SO4 is acid. Acid means it is a proton donor. It donates a proton. And after donating the proton, it becomes a HSO4 minus. So the HSO4 minus, if you look in the forward direction, H2SO4 is a proton donor. Therefore, this is an acid. If you look at the reverse direction, HSO4 minus is a proton acceptor. When you look at the equation in the reverse manner, HSO4 minus is a proton acceptor. Therefore, this is a base. Therefore, this is called the conjugate base of the acid H2SO4. Similarly here, look at HCl. HCl is proton donor. Cl minus is a proton acceptor when you look at the reverse reaction. So if you look at the reverse reaction, Cl minus accepts a proton and it becomes HCl. So Cl minus is a conjugate base. If you look at H3PO4, when one H plus is removed, H plus plus H2PO4 minus. So this is the conjugate base of H3PO4. And these two things, the acid and its conjugate base, are called conjugate acid base pair. Suppose any substance is given, you should be able to pair them up, which are the conjugate acid base pair. Now look at the water molecule. This is this water molecule combines with H plus to give H3O plus, or H3O plus gives a H plus and a water. Therefore, this is a proton donor, it is an acid. This is a proton acceptor and it is a base, conjugate base. Similarly, water itself can release one proton and it can be, and it can form OH minus. So in this reaction, H2O is acid and OH minus is a conjugate base. Look here, in the previous equation, the H2O acts as the conjugate base. In the second equation, the H2O acts as the acid. Therefore, one single substance which can act as an acid and also act as a base, they are called amphoteric substance. Amphibian-like. In zoology, amphibian means the animal which can exist both in water and on the land. Similarly, a substance which can act as an acid and also act as a base, depending upon the situation, is called amphoteric substance. Similarly, ammonia is also an amphoteric substance. Ammonia can donate a proton and can become NH2 minus, which is the conjugate base of the acid NH3. Similarly, NH3 can combine with H plus to form NH4 plus, that is the conjugate acid at the base, ammonia. So if NH3 as an acid, NH2 minus is the conjugate base, NH3 as a base, NH4 plus is the conjugate acid. Therefore, ammonia is also an amphoteric substance. So amphoteric means which can act as an acid and which can also act as a base depending upon the situation. So now look here. We want to define what is a strong and a weak acids. What's a strong and weak acids means? Take for example HCl molecule. HCl molecule is said to be a strong electrolyte. Why it is a strong electrolyte? It dissociates spontaneously. Even at higher concentrations, they exist in the solution in the form of ions. Why that dissociation is very spontaneous? Why it is able to give out the H plus ions very easily? The reason is the Cl minus ion. Look at the conjugate base. That Cl minus ion, you know the electronic configuration of a Cl. Chlorine outermost electronic configuration is S2P5. S2P5 is unstable, but S2P6 is stable. It assumes the inert gas electronic configuration. Therefore, chlorine is always in want of one electron. But here what happens? The Cl minus is stable. It is as stable as a noble gas. Therefore, the Cl minus attains stability. Anything which is more stable is less reactive. Therefore, that Cl minus is not in need of the H plus ion. Therefore, its attraction towards the H plus ion is very dull. Therefore, that is a weak conjugate base. So when the conjugate base is very weak, automatically the acid will be very strong. But look at the second case. This CH3COOH is a weak acid. Why it is a weak acid? If it donates, if it dissociates into H plus and a CH3COO minus, that CH3COO minus is not a stable ion. This is not stable. This is stable as long as it has the H plus ion. Therefore, this will not easily give out the H plus ion. This will strongly attract the H plus ion. Therefore, the conjugate base is a strong base. When the conjugate base is a strong base, then the original acid will be weak. Therefore, whether an acid is going to be a strong acid or a weak acid, that depends upon the nature of the conjugate base. So now look here, NaOH is a base, but it is not a proton acceptor. NaOH is not a proton acceptor. You look here, CH3COO minus is a proton acceptor. Similarly, Cl minus is a proton acceptor. But NaOH is not a proton acceptor, but it is a base. Why it is a base? In solution, it produces OH minus ions. In solution, it produces OH minus ions, and these OH minus ions are proton acceptors. They will accept a proton and form water. Therefore, directly NaOH is not a proton acceptor. That will dissolve, and the dissolved substance, a part of the dissolved substance is a proton acceptor, and OH minus ions accept a proton to form water. That is why NaOH is base. So you have to understand the difference between alkali and base. Base means anything which neutralizes acid is a base. But what is an alkali? Alkali is the alkaline earth metal or alkali metal hydroxides which are bases when they are dissolved in water. They are alkalis. You should understand the difference between alkali and bases. Bases are the substances which neutralize acids, whereas alkali are the hydroxides of alkali metals or alkaline earth metals whose solution in water are bases. So that is the difference between alkali metal and alkali and bases. Now look at this equation. With this derivation, we will conclude the class for today. This is called the Henderson-Hasselback equation. See, when you take a weak acid, this is a weak acid. Ha getting dissociated into H plus and A minus. Ba is its a salt. Say for example, this is acetic acid, this is sodium acetate. It's a salt. And I have already told you the salt of any weak electrolyte will be strong. Whether the combination is between a strong acid and a weak base, or a weak acid and a strong base, or a weak acid and a weak base, the resulting salt will always be strong because they all exist in liquid in the form of ions. So Ha is a weak acid which is getting dissociated into H plus and A minus, and Ba is its a salt which is getting dissociated into B plus and A minus. And you can write the Ka, that is the dissociation constant for the acid. Ka is H plus ion concentration into A minus concentration divided by Ha concentration. So from this you can find out what is the concentration of H plus, which is equal to Ka into Ha concentration by A minus concentration. Therefore, when you take a log on the entire equation, log H plus equal to log Ka plus log Ha by A minus. Now you change the sign everywhere. Minus log H plus equal to minus log Ka minus log Ha by A minus. What is minus log H plus? It is pH, because pH is the negative logarithm of hydrogen ion concentration. So pH equal to pKa minus log of acid concentration by salt concentration. Suppose if you invert this, if your salt is brought up and acid is brought down, this sign has to be changed. Therefore, I can write pH equal to pKa plus log of salt concentration by acid concentration. This equation is called Anderson-Hasselback equation, and using this equation only we were able to calculate the pH of buffer solutions. What are buffers and how buffers are trying to maintain the pH of a solution, and what happens to buffer in various conditions, that is EQ strength buffers are mixed. What will happen? Large volumes are taken, and all these things we will discuss in the later classes. And all the best. With this, I conclude today's class. So thank you very much. Thank you.